Okay, so you're learning three things about matrices today: determinants, identities, and inverses. Actually, there's a fourth thing. At the very end, you have to learn how to solve an equation that has a matrix in it. All right, so here we go. The identity is like this. In numbers, if I had the number 7, what can I do to a 7 that will allow it to keep its identity? Multiply by 1. That's using multiplying. Yes, 7 times 1 will keep its identity. What else can you do to a 7 that will let it keep its identity? Add a 0. That's the additive identity. So you can do those two different identities. You would think that with a matrix that you could simply multiply by 1, 1, 1, 1 and get the same matrix back again, but you don't. Let me prove it to you. I'll remind you how you do matrix multiplication. For this, I'm having a 2 by 2 times a 2 by 2. And these numbers match, so it's going to work, and my answer is going to be a 2 by 2. Would you please join me right now by making a matrix answer box and do the row 1 with column 1. Remember that deal? And match up the 5 and the 1 and the 4 and the negative 4 and the 1. And you multiply and you add and you put in an answer. So the 5 times the 1 makes 5 plus negative 4 times 1 is negative 4. Put them together, you got 1. Keep multiplying it out and get the answer, the final answer for this matrix. That spot there is row 2, column 1. Got all 4 numbers? What are they? Read them this way. There, 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 there. Kind of like a Z for Zorro. 1 what? 1. 9, 9. Raise your hand if you got the same thing he did. Awesome. And now, what did I just prove? I just proved to you that 1, 1, 1, 1 is not the identity. That will not be like 1. This is not like multiplying by 1 in normal numbers. That gives you something different. It did not keep its identity, see? But if you do this one, it will keep its identity. Prove it to yourself that when you multiply by this, the matrix actually keeps its identity. Row 1, column 1, 5 and 1 is 5, plus negative 4 and 0 makes 0. And my answer matrix is also a 2 by 2, and I get a 5 here. And that spot there is row 2, column 1. 1 times 1 is 1. 8 times 0. Oh, multiplying all the second numbers by 0. That's going to mean that it'll just stay as the first number. And there we go. 5, 1, negative 4, 8. Raise your hand if you got the same thing. Okay, good. What did I just prove? I just proved to you that this is like multiplying by 1. It allows you to keep its identity. So that right there, that is called the multiplicative identity. It's also the inverse. No, it's not. I'm sorry. It's not the inverse. It is the multiplicative inverse. I know that seems like it shouldn't be a big deal, but it is. Okay, so this is identity matrix. Remember how identities are kind of important? The word identity, as in it'll allow the matrix to keep its identity if you multiply by this thing. Why is the other one bigger? That's what you'd use for a what? 3 by 3. Very good. So to sum it up, that is kind of like 1 in matrix form. If you multiply by it, it's like multiplying by 1. It just keeps the matrix the same. Yes? Good question. There can be an identity matrix for many matrices, but not for all. All right, so we'll get to that. Does the order in multiplying matter? Like if you have 5 times 3, is that the same as 3 times 5? No, I'm talking about in normal numbers. 15, 15. Yeah, it's okay in normal numbers. In these, it does make a difference. They are going to be different answers. I'm going to prove it, or ask you to just prove it by doing only the first number. If the first number is different, you know the whole thing will be different, right? Just do the first number of each of these and see how you end up getting different answers. Just do row 1, column 1. Just do it for both of them. You'll see they start off with different answers, and therefore you know they're not going to be the same. So here's row 1, column 1. 5 times 1 is 5, negative 12. 5 plus negative 12, negative 7. That's important. You gotta be careful with your negative there. And then over here, row 1, column 1, 5 times 1, 2. 5 plus 2 is positive 7. Do you get that those are different? All right. Just do one more number to make sure for yourself that they are definitely different. Would you please figure out that lower left-hand corner number? What I'm asking you to do is row 2, column 1. That's even much more dramatically different. 25 and 16. So at first it might have looked like we just had one of them was the opposite of the other, like had negatives instead of positives, but it wasn't that. It's just different. So what's the moral of the story? Well, you can't just trust that if you multiply two things this way versus that way, that they're going to come out the same. Is there a weird case? Yes, it's this one. Only if you use these special identity matrices, then if you multiply on either side, it won't matter. You'll get the same thing. And I'll stop you from having to multiply this all out. It'd take forever. And trust me, at the end, you'd find that these do come out the same. But almost every matrix problem you'll ever do, if you do A times B, it will be different than B times A, except for this case of this weird identity thing. That's the one where you can multiply it either way and you get the same answer. What do you get when you multiply it? It's the identity. It allows this thing to keep its identity. So if you multiply this thing out, you'll get that back again. If you multiply this out, again, it's special. It can multiply on either side and it'll still work. You get this back again. You get the same exact answer back again. All right. So usually though, AB and BA are not equal to each other usually. With this special thing, it does actually work. But all right. Moral of the story, order matters on almost all the problems, so you need to be careful. If you say BA instead of AB, you're going to get a different answer. If you do them order, multiply them backwards. All right. The next thing is called a determinant. And what is a determinant? It's simply this. You take a matrix and you go like this times this, and that's going to be 40. And you go that times that, and that's going to be negative 4. And then you add them. No, you subtract them. Sorry. Forgot for a moment there. You cross multiply the two things, and then you subtract them. 40 minus negative 4, which really means 40 plus 4, which really means 44. What is a determinant good for? Well, there's a lot of things. I don't want to bore you with this. There's a lot of things you could use determinants of matrices for, but there's one thing that I'd want you to remember. It's kind of like this. Do you remember x equals negative b plus or minus square root b squared minus 4ac all over 2a? Do you remember how this part here was special? Because if we figured that out and it came out to a negative, then the whole thing doesn't work. Remember that? That was called a discriminant. This is called a determinant. When you do a determinant like this, if it ever comes out to 0, then you've got a problem matrix. That matrix won't work for things. You can't, for instance, solve a problem that's got that in it. It won't have an inverse. It has all kinds of problems. If the determinant comes out to 0, then you've got a problem. This guy's determinant didn't come out to 0. It came out to 44. So this determinant is a nice determinant. would you please, on the next slide here, do these two problems, get the determinant of this and the determinant of this one. One of them is going to be a problem matrix. Find out which one is the problem matrix. Just do them both. Write down both answers. Turn it my way and I'll tell you. Yep. It should be on your iPad, but I suppose if you don't have an iPad, that would be on. All right, there we go. Let me see your first matrix. Zoom in on them a little bit. Okay, good. Good, good. Getting some people with a negative 10 on the first answer and some with a positive 10. Be careful on that first answer. All right, let me show you. It's this times this minus this times this. So this times this is negative 8 minus this times this is negative 18. You get how the negative is important there? It's this minus that. And now if you go minus a negative, that's going to mean that it's plus 18. So the final answer is positive 10. My son in calculus class in college this year had his first experience with how college professors deal with a negative. He made the mistake on his test early in the problem, and so he lost every point after that because of the negative followed through, that whole mistake followed through. He lost 40 points on one of his tests because of one negative sign. Teacher said, well, you should have been more careful. So the point is, negatives are a big deal. In pre-calc, I swear I have kids that have C's right now that would have A's if they weren't careful with their negatives. Okay, negatives are a big deal. You're going to just be careful with them. So one of the prime times you have a problem is when you have a negative built into the formula, because people think, well, there's already a negative there. I don't need to use another negative. Well, if this number is negative, you've got to put negative 8. If this number is negative, you've got to put negative 18, and now the two negatives have to cancel each other out and make a positive, so yeah, it's a difference. Okay, 12, wait a minute, 12 minus 12, that's the problem matrix right there. Now what is a problem about it? It can't have an inverse if it's like that. So some matrices won't have inverses. If they don't have inverses, you can't get rid of them, and so you can't get them out of equations, which means they make equations impossible to solve. And so, anyway, all you really have to look for is if you ever do a determinant and you get a 0, you know you got a special matrix there that's going to mess you up. Yes? Yes, there's a way to do determinants on a 3x3, but it's much more complicated, and I'm going to show you how to use the calculator in just a minute, and the calculator can do it easy peasy. Yes?
Are you supposed to do that or do you just do it once it's find it?
If they ask to find the determinant, the answer would be 10 and the answer would be 0. So that's one time you'd do it. Another time you'd do it is if you were going to do the inverse by hand. I'm going to show you how to do that in a second. Then you have to have the determinant for that too. So the determinant is just multiply them crossways, cross product things, and then subtract in between them. Yes? You have to do it in order from left to right. Since this problem has this on the left and this on the right, it is negative 18, or no, negative 8 plus 18, and I have to go from left to right. How do I know that's on the left? Because these two have to be done first. Okay? All right. Moving on. What's an inverse? This is an inverse of this, but it's called an additive inverse. This is a multiplying inverse, and I'll give you one that's even better example. 3/4. What's the inverse of 3/4? 4/3. And then that's a multiplicative inverse. It's also called a reciprocal. it even confuses me sometimes because I've heard of reciprocal and I'm like, wait a minute, isn't that the same as the inverse? Not really, it's the same as the multiplicative inverse. This is an additive inverse. This is a multiplicative inverse. Anyway, multiplicative inverse and reciprocal are the same thing. And what's special about it is that when you multiply them, you get 1. Do you remember how I just showed you that matrices have a special way of making a 1? It's not just 1, 1, 1, 1. If you were doing a 2 by 2 matrix, the answer would come out to that. That's the matrix way of saying 1. Okay? All right, so two things that are inverses will multiply together and equal 1. All right, this is the really complicated formula you'd use to find the inverse of a matrix. It's not as bad as you might think. That right there, that's the determinant. Remember we just showed you how to do determinant? This times this, minus, that times that. That goes there. That's the determinant. That's why, do you remember me saying that if you had a 0 determinant, you'd have a problem? Because now you'll have 1 over 0, and that crashes it. So that's why if you ever do a matrix problem and you get a 0, that you can't go on. I mean, it's going to cause you to have issues with your inverse and all kinds of stuff. Okay, and then to finish that, you have to take A and D and reverse them. See how D is up there and A is down in the corner? And then see how C and B are? They're the opposite of what they were. So it's kind of complicated. It's got it spelled out here. If you wanted to do the inverse of this by hand, first you find the determinant, then you stick the determinant down here and go 1 over the determinant, and you times it by, these two numbers got switched their places, see, from where they were, and these two numbers are the opposite of what they used to be. So it's not like it's impossible to do, but it's kind of a pain in the butt to do. And the final answer comes out to this. In a minute or two after lunch, I will show you how you would get that on the calculator. And we're not quite ready for lunch yet, about 1 more minute. So why don't you just get your calculator and see if you can put this into matrix A. All right, so first to do that, you need a matrix, find the matrix button. So get your graphing calculator and go to, I'm going to clear my screen here. Matrix is right up in there. See the button that I just turned red? It's above that button is where matrix are. And we're going to put in matrix A, so we need to edit matrix A. So the first thing you do isn't, if you hit enter, what happens is it puts an A on your screen. You don't want that yet. You haven't told it what A is. So clear that off and go into matrix and go over to edit matrix A. We want it to be a 2 by 2, and then you enter 2, 2, 2, and 4, just like I have it in here. You just type in 2 and 2, and then type in 2, 2, 2, and 4. And you'll know you did it right, and you'll be able to go to lunch as soon as you have typed this in, and then quit out and put matrix A on your calculator and hit enter, and you'll have 2, 2, 2, 4, just like that. Hold it up if you already got it. You can go to lunch. 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 Go to lunch. Go to lunch. Go to lunch. Be there in 2 seconds. See? We go. Okay, we're back from lunch, and we just had guys put this into the calculator, and you got that in your calculator, right? Now, if we want to do that long, complicated process by hand, go ahead, but I don't want to. I want to do the inverse with the calculator. So here's how you do it. Everybody go back to second matrix. So you're in the matrix menu. You're in the matrix, yes. It's a good movie, too. And you hit enter. That brings the A up on the screen. Don't hit enter again, though. We just want the A on the screen. Now we want to go A to the power of -1, and there's a button for that. Like there's an app for that. There's a button, one touch button right there. The same place where the matrix is actually, right above that. So we want to the -1 power, that means inverse. And then all I have to do is hit enter. It does all the calculations, and there it is. There's your answer. Now, if that's really the inverse, what should happen is, if I take that times the original one, I'm supposed to get 1. right? That's what inverses do. Times the two inverses together, you're supposed to get 1. But remember, the matrix version of 1 is that triangle one that or the matrix that goes like this. I'm talking about that's what 1 is. So I want to prove to you we actually found the matrix of the inverse. So take this times the original matrix, which was what? A. And I've got to find that under the matrix menu and hit enter. That way it brings up an A. And so it brought me the inverse times A. And if I hit enter, it gives me 1001. That means that those two really were inverses, because when I multiplied them, I got the 1 matrix. Okay? All right, so your problems are as simple as find the matrix of this and find the matrix of that, or find the determinant of this, or find the determinant of that. So let's get one more. Let's try determinant. Go back into the matrix menu. Where do you think functions like determinant would be? Not here, clearly. Math, you got it. Math. And which one do you think is determinant? The DET. So today, DET. Now, how do I get the A matrix here? Yep, second matrix, A. Determinant of A. And the parentheses, and you'll have it. Enter. The determinant of that was 4. That's the cross products thing where you go this times this and that times that, and you subtract them. The answer is 4. All right. Would I expect the answer to have been 0? No, because this one had an inverse, remember? If you ever get one where the determinant is 0, that's a problem matrix, and it won't have an inverse. Yes? All right, your calculator is different then, so I'll talk to you about that later. All right, now let's move on to the next kind of problem here. Do you get how you would use inverses to fix this equation? You want to get rid of the 3, what would you use? Not divide by, multiply by 1/3. See, the reason we can't use divide by is because matrices you can't divide. So I have to multiply by something. How do I multiply to fix that one? 5 halves. If I multiply by 5 halves on both sides, it'll fix it, right? Cancel, cancel. Same thing here with matrices. If you use the inverse matrix, you can cancel off a matrix. So take a look at this. Do you get how I want to get this xy alone? So how do I get rid of this thing right here? By multiplying by its inverse. So I'd put that into the calculator. I'd figure out what the inverse was. That's the one we actually did, right? Once I found its inverse, I would multiply by that on both sides. And what was it again? What? 1, negative a half, and then negative a half, and then a half. Or 0.5 would have been fine. Anyway, there's my inverse. What this does when I go that times that is it makes it effectively turn into a 1. That's the same thing. It gets rid of it, you know. But if I do it on this side, I also have to do it on this side. But why would I get it wrong if I did this on this side? Somebody be picky. Math is picky. Yes. Because this times this isn't in the right order. I did the matrix on the left side. I have to do this matrix right here on the left side or it won't work. Remember how the order matters? If I'm going to multiply this guy by this, and I did it on the left of it, then I have to do this one on the left of it also. All right, you aren't going to even have to solve anything that hard today, but I wanted to give you the big picture because the research proves that then you'll be better at this tomorrow when I show it to you for real. But right now, all you really have to do is be able to find inverses of matrices and determinants of matrices, and it's going to be super simple because you can use a calculator for most of it. All right, this one, I'm not even going to pain you to put that in the calculator and do to the power of -1. Just remember you'd use this button, x to the -1. You use that button on it, and it puts this on there, and then you hit equals, and it gives you the answer. So inverses are very easy on the calculator. But this kind is the last kind I need to show you, because that's the kind that's going to be probably harder for you on today's homework. The last 2 problems are like this. And there's questions on the test that'll be like this, of course. The point on this kind of problem is to solve for A. Would you please turn your iPad and show me that you're in the right spot? If you're not in the right spot, I would like to talk to you later about why you're not in the right spot. I'm waiting. I'm waiting. I'm waiting. Okay. Thank you. Please get in the right spot. Thank you. All right, here we go. Now I'm going to add 2, 2, 2, 4 to both of these. Everybody do that. Why am I doing that? Because I'm trying to get the A alone. This and this will cancel each other out. Those are called inverses of each other, additive inverses of each other. So I'm just simply subtracting here. This is not that inverse thing. This is a simple add, subtract difference. This was subtracting it, so I'm adding it to both sides. Now this is the easiest of all matrix problems, so you should be able to do that in your head. 2A equals 6 plus the 2 makes 8, 10 plus the 2 makes 12, 14 plus the 2 makes 16, 16 plus the 4 makes 20. Get what I just did there? All I did is add that matrix, 2, 2, 2, 4. Now how do I get the 2 off of there? And remember, you can't divide in matrix land. Times by 1/2, very good. Times by 1/2, and remember, if you times by things in matrix world, you have to do them in the same order. So if I put the 1/2 on the left side, I gotta put the 1/2 on the left side. I know that's really picky, and in this case, it may not have even mattered, but you gotta make sure you do these in the right order when you are getting to the more complicated ones. All right, that cancels that, and A is alone. Yay. And if you can just simply multiply everything in there by 1/2, you'll have it. This is called scalar multiplication. When you just multiply by one number, it's super easy. So 1/2 times 8, 4. 1/2 times 12, 6. 1/2 times 16, 8. 1/2 times 20, 10. There is the answer matrix. All right, that was one I did mostly with you. Try that one. The next problem on your slides. That's the last problem we're doing together. Try it. See if you can handle it. If you get stuck, I'll give you a hint in a minute. All right. You should have started by adding 1, 2, 3, 4 to both. I would do it this way if I had room. That'll cancel that. And then I have 3A equals 30, 30. 9 plus 3 is 12, and 18. Would you please turn yours my way when you think you have the answer? Yup, 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 yup. Nope. Yup, yup. Yup, yup. Yup, 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 yup. Yup, yup, yup. Yup. Judging by the tremendous number of yups you guys knew what to do, you multiply by 1/3 on both sides, and that means you're taking 1/3 of each number. That would be 10, 10, 4, and 6. 10, 10, 4, 6. Raise your hand if you had that one right. That's almost everybody. Okay. Then just one last thought. This is what we're doing tomorrow. How would I get this off of here? I would multiply by its what? Inverse. And once I found that inverse, I'd multiply it on both sides, but I got to be careful. I got to do it right there because it's got to be the left side of both of them. Then this would cancel, and this becomes x over y, no, in a matrix, equals, and then once it's all multiplied out, your calculator can do the work. It can do this one times this one, and it can tell you the answer. And the answer will be something like this, 3, 7, and then it's like, oh, x is 3 and y is 7, see? That's what you're learning how to do tomorrow. But up to this is the hardest thing we're going to have to do on today's worksheet. All right, so find the homework for today. Everybody look for it. It's under today's date. Today's date is the 29th. Yes, sir?
Why does the order matter?
Why does the order matter? Because when you do it in a different order, it rearranges the numbers. And when it rearranges the numbers and you have to multiply by them, you get different answers. I tried to prove that to you with a couple example problems, but bottom line is it rearranges the numbers because of how we have to match up rows and columns. So, okay. And that's all I've got for you for today.